This is a typical look of a hydrogen atom orbital with the peculiar lobe-like structure that actually arises from the spherical harmonics, which are nothing but standing waves on the surface of a sphere. To understand this, let's first take a look at the spherical coordinate system. The radial solution gives us variation with respect to radius. The angular solutions gives us variation as we go from north to the south pole, and the azimuthal solutions gives us the variation as we walk along the equator. If we somehow plot functional values on the surface of the sphere, then we will get something that looks like this. You see? Where the different colors represent different values. The reds represent negative value, the blues represent positive value, and the whites represent zero value, where the eventual wave function will go to zero. Now, this is nothing but a standing wave on the surface of a sphere. We can all visualize a standing wave on the surface of a plane. But what if that plane surface is wrapped around a sphere? This is exactly similar. The only difference is that we have plotted the mathematical value of the function as a color here. But if instead of the color, we represent the value of the function as distance along the radius, then suddenly we get this beautiful shape. These represent the directions of probability densities, where the electron density will eventually have some positive value. And therefore, they are the origin of the peculiar orbital shapes that we see in hydrogen atom. The hydrogen atom is the crown jewel of Schrödinger's quantum mechanics. It is one of the simplest realistic problems in nature that we can analytically solve using quantum mechanical theory and get exact solutions. And that is what I'm going to do in today's video. From start to finish, I'm going to use the Schrödinger's quantum mechanical theory to obtain detailed solutions about the energy eigenfunctions, energy levels, and the nature of the probability densities. I'm going to make it as detailed as possible. I have seen that in many quantum mechanics textbooks, when it comes to this particular derivation, the author usually skips a particular number of steps and gives you the final result. I have made a lot of effort to avoid that, so that I can in this video give you a step-by-step solution of the entire problem from start to finish. I hope that you will appreciate the effort that I've put in today's video. I have divided the entire video into different timestamps, whether it is visualizing spherical harmonics, whether it is the Laguerre polynomials, whatever you want, the timestamps are there. You can jump to whichever part of the solution you are interested in. You can also change the speed of the video to 1.25x or 1.5x if that helps you to go through the entire length of the video. So let us go into a journey of deep mathematical calculations and physical insights that is nothing short of an achievement of modern physics. The hydrogen atom is the simplest atom in the periodic table. It consists of a very heavy, positively charged proton nucleus and a very light, negatively charged electron. The nature of the interaction between a proton and an electron is given by Coulombic interaction. And the potential energy function between both of them leads to an expression VR equals minus E square upon 4 pi epsilon naught R. This is a 3D problem because the electron can be found in the three-dimensional vicinity of the proton. And because we are dealing with a spherically symmetric potential, for our calculations, we will be using, therefore, a spherical coordinate system. In a spherical coordinate system, instead of the coordinates x, y, z, we will be using the coordinates r, theta, and phi. R is the radial distance from the origin. Theta is the angular displacement with respect to the north pole of this particular diagram. And phi is also the angular displacement along the equator. We will be relying on defining every single point in this vicinity with respect to r, theta, and phi. If you look at the nature of this particular coordinate system, it is obvious that the radial magnitude can go from 0 to infinity. Theta, the angular displacement, can go from 0 to pi, and the azimuthal angle phi can go from 0 to 2 pi. We are ultimately interested in solving this particular problem to obtain the wave function solution. The wave function solutions can be written in its general form as the eigenfunction solution, which is a function of r theta phi, and of course the time dependent part that can be written as e to the power minus I e t upon h cut. What we will be doing today is to obtain the general nature of these eigenfunction solutions. And ultimately what we would like to do is use the eigenfunction solutions that we obtain and find out its mod square, because that will give us the probability density of the electron being found in the hydrogen atom, which will lead to the standard orbitals and atomic shells that we study. So to do that, we will start with the time-independent Schrodinger equation in 3 dimensions with respect to a spherical coordinate system. Minus h cross square, nabla squared psi plus v psi equals e psi. Almost all of you are probably familiar with the Schrodinger equation at this particular point in time. The only difference you would see here is because we are dealing with the spherical coordinate system, the nabla squared has this particular expression for the spherical coordinate system. This leads to the detailed shape of the Schrodinger equation, which is minus h cross square upon 2m 1 upon r square del upon del r square of del psi upon del r plus 1 upon r square sine theta del upon del theta sine theta del psi upon del theta plus 1 upon r square sine square theta del 2 psi upon del phi 2. Now, at this particular point, it is going to be clear to you that we are going to be dealing with extremely lengthy mathematical equations. So here I have v psi equals e psi. This simplifies to, if I take the negative sign from here, instead of writing the entire expression, I can just introduce the negative sign here and the negative sign here. If I rewrite the expression again, this becomes v minus E psi, where V is the potential corresponding to the Coulombic interaction. And I can also take these constants from here to 2m upon h cross square. That's it. This is equal to 0. Now, to solve this kind of a problem, we will be using something called separation of variables method. You see, the eigenfunction solution here is effectively a function of 3 distinct variables, r, theta, and phi. Now, what we can do is we can separate the functional dependence on r, theta, phi into 3 distinct functions. That way, we can simplify the second order partial differential equation into 3 distinct ordinary differential equations. So the eigenfunction solution psi of r, theta, phi can be assumed to be the product of a function r of the radial distance, a function theta of the angular displacement, a function phi of the azimuthal displacement. Here, R function is basically known as the radial solution, and theta and phi are combined as y theta phi, known as the spherical harmonics. We will need to solve each of them individually and understand the detailed nature of its solutions to appreciate the final solutions that we are going to get. So these are spherical harmonics. So when I substitute r and y in our above equation, let me say that this equation is equation number 1, then the equation further simplifies. So instead of writing everything together, let me copy and paste it here and just simplify it further. So instead of psi, I'm going to write r and y here. If I divide the entire expression by ry, what I'm going to get is this will be gone from the last term. In the first term, the y will be gone and I will be left with 1 upon r here, capital R. In the second term, r will be gone and I will be left with capital Y here. And also in the third term, I will be left with capital Y. Okay. So all of this can further be simplified as, and if I take the small r square from the denominator of all these first terms to the last term, I end up getting 2mr square upon h cross square. Here, v is a function of r minus e, which is basically constant because it represents the total energy of the system. Now this can further be simplified by separating the functions of r and the functions of theta and phi. So if I separate the functions of r, this becomes 1 upon r del r square del r upon del r minus 2mr square upon h cross square vr minus e. And in the right hand side, we will have, I'll just have to introduce a negative sign here. So the left hand side is entirely a function of r, the radial distance, and the right hand side is entirely a function of theta and phi, which are the angular and the azimuthal displacements. As a result, we can conclude that this entire equation, there should be a negative sign here, must be equal to a constant, because these are independent variables and the equation consists of functions of independent variables, and because they are equal, the only conclusion here is that the left hand side of the equation is equal to some sort of a constant L plus 1. If I do that, then the right hand side of the equation is also equal to the same constant. So here, if I take this negative sign out, then I end up getting minus L plus 1. Now you may have a question at this particular point, that why have I taken the constant to look something like this? You see, the hydrogen atom is a standard problem in quantum mechanics that has already been solved, and the nature of the solutions is already known to us. And we will see that the differential equations that we get in our calculations will effectively lead to certain very special functions known as Legendre functions, as well as other similar polynomial functions, which can be written effectively in a much more simpler standard manner if we do consider the constant to have this particular value. You see, at the end of the day, the right hand side is a constant. I could have written C or I could have written anything else. It doesn't matter. The constant is effectively some kind of a value. This is only going to help us in rewriting the final solutions in a certain manner. So what is L here? We will again find out. We will discover the values of L at a later point in our discussion. Now what I want to do is, because I have effectively separated the original Schrodinger equation, which contained psi, which is essentially a product of radial solution and spherical harmonics, we have divided that particular differential equation into two distinct differential equations. I'm going to say this is equation number 2 and this is equation number 3, we need to look at these differential equations separately. The detailed solution of the radial part of the Schrodinger equation is a little bit lengthy, so I'm going to do that at the end of the video. First, I want to look at equation number 3. So let's look at the angular equation, which is the part of the Schrodinger equation that contains theta and phi. This is the angular equation where we can further apply the concept of separation of variables method. So what we are going to do is, here we will again use the concept of separation of variables. As I mentioned earlier, the spherical harmonics are the functions of theta and phi together. So I can write y, the spherical harmonics, as the function theta of the variable theta and the function phi of the variable phi. If I do that, this can be further simplified. Okay, so let's try to do that. So if I multiply both sides with y sine square theta, here I'll get sine theta del upon del theta of sine theta del y upon del theta plus del 2y upon del phi 2 plus L plus 1 y sine square theta is equal to 0. Because y is in terms of theta and phi, so further what we can do is, now I want to divide the entire equation by theta function and phi function. If I do that, this term will vanish in the last expression, and in the first and the second expressions, I will be left with 1 upon theta function here and 1 upon phi function in the second term. Now we will end up getting a similar solution where if I rewrite everything in terms of the functions of theta, it becomes equals minus 1 upon phi function del 2 phi function upon del phi 2. So you see here, we have again separated this angular equation part of the Schrodinger equation into the left hand side, which is a function of the theta variable, and the right hand side, which is a function of the phi variable, which are independent variables. And the only way the function of one variable and a function of another variable which are independent can be equal is if they are equal to some constant. So now we end up getting two more differential equations. One is the theta part of the differential equation. Let's say that this is equal to a constant which is equal to m squared, and the phi part of the differential equation del 2 phi function upon del phi 2, which is basically equal to, because there is a negative sign here, it will be equal to minus m squared. Now again, you can ask the question why we have taken the constant to have this particular form m squared, and the answer goes back to the standard solutions that we are hoping to get at the end of our derivation. Those solutions will have a better form if we do take this constant to look like this. So let me rewrite this equation as point number 4 and 5. So we have successfully separated the original Schrodinger equation, which was a partial differential equation containing functions of theta, functions of r, functions of phi, into three distinct differential equations. Equation number 2, which is the radial equation, and equation number 4 and 5, which are the angular and the azimuthal equations. Let us solve them one by one. Many of my Indian students who are in college and university have to appear in competitive examinations to get into premier research institutions and IITs, and also to be eligible for lecturership jobs. We at Elevate classes regularly organize live as well as recorded courses for those students who are looking for a very dedicated batch for that kind of a preparation. If you are one of those students who are looking for guidance, then you can join with us for your preparation. We regularly launch live batches, so check our website for the next live batch to start. We also have recorded content that you can access anytime from anywhere. So explore all our courses at elevateclasses.in. Back to the video. So now we solve the azimuthal equation, which is the easiest out of the three differential equations that we have to solve. So this is d2 function psi upon d psi 2, because the function psi is a function of a single variable psi. Therefore, the partial derivatives becomes an ordinary derivative, plus m square psi function equals 0. Now, at this stage in our learning of quantum mechanics as a subject, you must have seen these kinds of differential equations over and over again. When we were dealing with problems like free particle, particle interacting with a step potential, infinite potential well, etc., you should have seen these kinds of differential equations, and by now, the standard solutions of differential equations like this should be very obvious. Okay, so what is the solution for a differential equation that looks like this? The standard solution is of the form of phi equals, let's suppose, some constant a e to the power iota m phi variable. Now, of course, solutions contain both e to the power positive terms as well as e to the power negative terms when we look at the general solution of this kind of a differential equation. So if we assume that the constant that we are dealing with here, the constant which is m, can take both positive and negative values, then we can simply absorb the positive negative sign to write that the solution phi equals a e to the power iota m phi. That's it. Of course, we can normalize here to get the value of the constant. So if I say that I take phi function, complex conjugate phi, and integrate with respect to the variable phi from 0 to 2 pi, because that is the bound or the range of phi here, and this is equal to 1, this calculation will give us the value of the normalization constant. So we will get a square e to the power minus iota m phi and e to the power iota m phi, which, by the way, gets cancelled, right? Which is equal to 1. So essentially you are integrating phi from 0 to 2 pi. Such an integration will just give you 2 pi, nothing else. So a square 2 pi equals 1. And as a result of it, a is simply equal to 1 upon root 2 pi. So the detailed azimuthal solutions that we have obtained looks like this. Phi is equal to 1 upon root 2 pi e to the power iota m phi. That's it. We have obtained the first part of the wave function solution, which is dependent on the azimuthal angle phi. Now, if you take a look at our original coordinate system, where I explained to you the variation of r theta phi, then phi essentially is the angular displacement if you sort of move along the equator. Yeah. So if you go along the equator, that is when the azimuthal displacement of phi takes place. And every time you move around the equator, you complete one revolution of phi equals 2 pi, then you come back to your original location. Using this idea, we can calculate the value of the constant m. Yeah. So when you complete one revolution along the equator, you come back to your original point. So phi, after doing one complete revolution of 2 pi angle, then that is going to give us the same functional value, because we end up coming back to the same point in 3D space. So if I write this in a detailed manner, this becomes 1 upon root 2 pi e to the power iota m phi equals 1 upon root 2 pi e to the power iota m phi plus 2 pi. We can simplify this to get the value of m. How can we do that? Well, let's take a look here. This is how we proceed. So e to the power iota m phi equals e to the power iota m phi times e to the power iota m 2 pi. Of course, I can cancel out this term e to the power iota m phi, and therefore we are only left with e to the power 2 iota m, or I should say iota m 2 pi, or 2 pi iota m equals 1. Now, how can you write this kind of a oscillatory function? Right, this is an oscillatory function that can be written in terms of sines and cosines. So if you have e to the power iota something, that can be written as cos something. So here the cos is nothing but 2 pi m plus iota sine 2 pi m equals 1 plus 0 iota. So we can make a comparison of the real part and the complex part to get an idea about the value of small m. Here cos something is equal to 1 will give us solutions where 2 pi m is either equal to 0 or 2 pi or 4 pi and on. While on the other hand, sine something will give us 0 for solutions which are 2 pi m is equal to 0, pi, 2 pi, 3 pi, 4 pi, etc. So we will only consider those solutions that will give us effectively this particular equation, right? And if you look here, those common solutions are 0, 2 pi, 4 pi, and on, thereby giving us a way to calculate the value of m. That is, 2 pi m is equal to 2 pi times an integer, where the integer will include values like 0, 1, 2, 3, like that, where m is equal to 0, 1, 2, 3, and on. And just some moments back, we included both positive and negative values into the value of m. So therefore, we have to allow for both positive and negative values given the manner in which we did the derivation. So therefore, m can take the values of 0, plus minus 1, plus minus 2, plus minus 3, and on. So there you have it. We have obtained the azimuthal solutions, which are that part of the wave function solution which only gives us information about the variation of the wave function along the equator, if we walk along the equator, which depends upon this particular quantum number m that can take values of 0, plus minus 1, plus minus 2, plus minus 3, etc. This is an important quantum number which is necessary to specify the state of a hydrogen atom, also known as the magnetic quantum number. Later on, when we study angular momentum, in a different video, of course, we will see the role that this kind of a magnetic quantum number plays in terms of the angular momentum of the electron in the hydrogen atom. What this m magnetic quantum number does is, it gives us an idea about the z component of this angular momentum. So in a way, the magnetic quantum number is very much responsible for what is known as direction quantization of angular momentum. But before we move forward, I want to give you a visual representation of these solutions. How do they actually look like if I plot them in a graph? So let's take a look at that. There you have it. These are the visual plots of the azimuthal solutions. Now keep in mind that if you're trying to visually look at the azimuthal solutions, you will have both the real part and the imaginary part. You can think of the azimuthal solutions as that part of the wave function solution, which you see when you look down on this particular sphere. Okay. We have radial solutions along the radius. We have angular solutions, which basically are along a particular angle subtended with respect to the north-south axis. But for the azimuthal solutions, you are essentially looking at the solutions as you go around the equator. So think of looking down on the sphere from the North Pole. Okay, that is how you see the variation. And this is the variation visually represented in these graphs, which is kind of interesting because we see the wave nature of these solutions immediately. So for example, for the magnetic quantum number 0, you essentially get a constant value. And when you increase the magnetic quantum number 1, instead of having a constant value, now you end up seeing this one complete oscillation along this particular plot. When you go to m is equal to 2, you see two complete oscillations along this particular plot. Yeah. When you go to m is equal to 3, you see 3 complete oscillations around this particular plot, both in the real plane and in the complex plane. Of course, the real part and the complex part are out of phase. This is an interesting behavior that we actually see because as I keep on increasing the magnetic quantum number, the windings of the function around this particular plot keeps on increasing by 1. And the reason is that the value of this particular magnetic quantum number is directly linked to the angular momentum component along the z-axis. And with increasing magnetic quantum number, we end up getting increasing value of the z component of angular momentum. Here, these azimuthal solutions, they essentially represent phase rotations. And even though they do not participate in the overall probability density, because when I will finally take psi mod square, this will get cancelled out, it does carry important information in terms of angular momentum and also in other kinds of cases like interference, bonding, etc. So now that we have successfully obtained one part of the wave function solution, let's move on to the angular part, which is the theta part of the spherical harmonics. So now we look at the angular part of the Schrodinger equation, and we will try to obtain a solution of the wave function that is dependent on theta. So for that, we have here equation number 4, which we obtained earlier. So if I call this the angular part, then let's do the calculations. Simplifying this equation is not very difficult. The partial derivatives will become ordinary derivatives because it's a derivative with respect to theta, and the function is a theta function of variable theta. Further simplifying this, I can take the theta function to the right hand side, and this is going to give us sine square theta d2 theta function upon d theta 2 plus sine theta cos theta d theta upon d theta plus L plus 1 sine square theta minus m square times the theta function. Okay, all right. Now this is a very special kind of differential equation which has the form of what is known as a Legendre function, or more specifically an associated Legendre equation. But the standard form of the equation is not written in terms of theta, it is written in terms of x. So I am going to do a couple of calculations, substitutions to obtain the standard form of the associated Legendre equation from this particular equation forward. So for that, we will make a few substitutions where I say that cos theta is equal to x, and the theta function, which is a function of theta, I'll call it as y, but y is a function of cos theta. So from here, it is kind of obvious that dx upon the theta equals minus sine theta. It is also obvious that if I take derivative with respect to theta, it can be written as derivative with respect to x times dx upon the theta. So therefore, this becomes dx upon the theta is minus sine theta d upon dx. And if I also do a derivative of the theta function with respect to theta, because the theta function is y, so I can write dy upon dx upon the theta, which I'll again substitute with minus sine theta. So I end up getting minus sine theta dy upon dx. This gives us the possibility of obtaining the second order derivative with respect to theta function, which is d upon the theta of d theta function upon the theta, which is equal to d upon the theta of minus sine theta dy upon dx. So this becomes minus sine theta. The one of the terms will be this, the other term will be d upon dx of dy upon dx times dx upon the theta dy upon dx, and d upon the theta of sine theta is cos theta. So this becomes minus cos theta dy upon dx. And what is dy upon dx upon the theta? It's minus sine theta. So this becomes minus minus plus sine square theta, and you're left with d2y upon dx2. All right, so we have these expressions which I want to substitute in our equation number 4. So I'll consider this to be the equation number 4 only, because it's after all just a mere change from the original equation number 4. So if I substitute these values in the equation number 4, then what do I get? Let me just copy this and I can make the necessary substitutions here. So from equation number 4, we have, so sine square theta, what is d2 theta upon d theta 2? It is nothing but minus cos theta dy upon dx plus sine square theta d2 upon dx2 sine theta cos theta, and this original term we have minus sine theta dy upon dx. So my intention here is to obtain the standard form of the associated Legendre equation so that I can then implement the standard solutions that are known in mathematics for that kind of a equation. This should be y, and this is equal to 0. So let's look at all the terms again. I have minus sine square theta cos square theta dy upon dx plus sine to the power 4 theta d2y upon dx2 minus sine square theta cos theta dy upon dx plus L plus 1 sine square theta minus m square y equals 0. So here this finally becomes, let's write this particular term first. So I can cancel out the sine square term, right? Okay, let me remove the sine square term. So if I remove the sine square term, I'll remove it from here, 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 and I'll put a sine square theta term here, right? So if I make these changes, I will end up getting an equation that looks something like this. So we have sine square theta d2y upon dx2, and then you have minus 2, sine square theta is gone, we have cos theta dy upon dx plus l plus 1 sine square theta minus m square upon sine square theta. By the way, this sine square theta is gone, right? This is gone, so I don't need this. And there you have it, the final equation corresponding to the angular part of the Schrodinger equation. Of course, because I've taken x is equal to cos theta, so therefore this can be written as x square is equal to 1 minus cos, 1 minus x square can be written as 1 minus cos square theta. Therefore, 1 minus x square equals sine square theta, right? I can implement the sine square theta with 1 minus x square. So the equation finally becomes 1 minus x square d2y upon dx2 minus 2 cos theta is nothing but x, so this is 2x dy upon dx plus l plus 1 minus m square upon 1 minus x square, y equals to 0. This is known as the associated Legendre equation in mathematics. It can also be rewritten in a slightly simplified manner as the interesting thing about this associated Legendre equation is that the standard solutions are already known to us. Now, of course, we can go ahead and try to solve this differential equation in our own. That itself will take a certain amount of time because then that becomes a mathematical problem. I will avoid that given the lengthy nature of our video. I will just use the standard solutions of the Legendre equation that is already known to us. So here we can write yx equals some kind of a constant PLMX, where PLMX is associated Legendre function, or because yx is also equal to theta, as I've already made that substitution. So theta function with respect to the theta variable is equal to a PLMX is equal to cos theta. Okay, there you have it. This is the associated Legendre function. Here are the detailed nature of the solutions. So here you have the associated Legendre equation, right? Which is what we obtained earlier. And the solutions of the associated Legendre equation are given by the associated Legendre function, which is written in this particular manner. That involves taking multiple derivatives of what is known as the Legendre polynomial. And the Legendre polynomial is given by the Rodriguez formula. So effectively, we get polynomial solutions of this differential equation. Now, I would like to spend a little bit of time trying to understand the mathematical solution as well as the graphical solution to this particular equation, because that will give us an intuitive idea of how the orbital shapes of the hydrogen atom actually end up arising in our final solutions. So if you take a look at the Legendre polynomials, in the Legendre polynomials, the subscript L essentially represents the order of that particular polynomial, right? It can take the value of 0, 1, 2, 3. And as a result, it also gives us an idea about our constant that we have chosen initially, the particular L value. So let us take a look. What would be the different polynomial solutions for the Legendre polynomial. So if I choose, let's suppose P0x, right? So if I take P0x where L is equal to 0, then of course this ends up becoming 1 upon 2 to the power 0, 0 factorial, d to the power 0, dx to the power 0. Here you have x square minus 1 to the power 0. So there is no derivative. This is 1. The 0 factorial is 1. 2 to the power 0 is 1. So you end up getting 1. All right, fine. What if I take the first order, L is equal to 1? Then of course you end up getting 2, 1 factorial, and d upon dx of x square minus 1. If I solve this, I will end up getting half, and this is nothing but 2x. So essentially I end up getting x. Yes, so this is how we can generate the Legendre polynomials and then the Legendre functions, and then we can get a picture of the solution of the angular part, right? Now if I go to P2, this is of course 1 upon 2 to the power 2 times 2 factorial d2 upon dx2 x square minus 1 to the power 2, which can be simplified as 1 upon 8 d by dx of d by dx of, so this is x to the power 4 plus 1 minus 2x square, which ultimately becomes 1 upon 8 d by dx of 4x cube minus 4x, and further it becomes 1 upon 8. This is 4 into 3, 12x square minus 4. This ends up becoming, so I can write 2 here. This becomes 3x square minus 1. So there you have it, the first 3 Legendre polynomials. So here we have the first 5 Legendre polynomials that you can obtain using the Rodriguez formula. Okay, now this is the Rodriguez formula used to obtain the Legendre polynomials that I am writing here on the side. Okay, if you're interested, you can check each one of them yourself. But keep in mind that x here, because we are substituting cos theta with x, right? Initially, cos theta with x. So these polynomials are actually with respect to cos theta. So x is equal to cos theta, right? And once you rewrite these polynomials in terms of theta, then further you can substitute them in this particular equation, because these are the Legendre polynomials here, to obtain the detailed solutions. Okay, and if I do that, then the solutions that I will get will look like this particular table. So here I have a table of the various solutions. Okay, I hope that you will appreciate that I'm providing you this table. If you want, you can check them yourself. You can find out every single polynomial from this Rodriguez formula. You can use this and substitute it here in the Legendre function expression and obtain the detailed nature of the Legendre function solutions. Here, of course, every single function is associated with a value of L, right? And a value of M. We have already got an idea about the magnetic quantum number M. It can take values of 0, plus minus 1, plus minus 2, plus minus 3, like that. L, because we know that this represents the order of the Legendre polynomial, can take values of 0, 1, 2, 3, 4, like that. It would be interesting to see how they would look like in a graphical representation. So for that, I have prepared a couple of graphical plots that I am sure that you will find very interesting. Let's take a look one by one. So first of all, here I have these plots of these Legendre functions, but with respect to two different axes. Okay, usually whenever we study these Legendre functions, we study it with respect to x in this particular manner, right? So we study with respect to PLMX, and their values can go from +1 to -1, right? But we are also making a change of studying from x to cos theta. So that would represent a certain difference that arises in the plots. Let's take a look at that first. So here in this graph, I have for you, in the left-hand side, the original Legendre functions, the associated Legendre functions with respect to x. As you can see, in the y-axis, the values go from -1 to +1, and in the x-axis, the values go from -1 to +1 as well. Now, the moment I change from PLMX to PLM cos theta, now the scaling gets affected a little bit because cos theta values here, theta goes from 0 to pi. Keep in mind that we have already defined what theta is when we were first establishing our spherical coordinate system, that theta is the angle that your radial vector makes with respect to, let's suppose, the north pole here. So think of this as the north pole, and think of this as the south pole, right? So if I can draw some kind of a straight line from the north pole to the south pole, the radial vector is going to make an angle theta with respect to the particular line. Yes. And as theta goes from 0 to pi, it traces out that particular region. Yeah. So you can imagine that as theta is increasing, you're walking along a particular longitude along the earth or along this particular sphere. So the associated Legendre functions has a functional value as we are going from theta equals 0 to theta equals pi. So when I transform the standard associated Legendre functions in terms of x to in terms of theta, then there is a slight modification in the plots. Yeah, I hope you can see this from the visualization here. These are the original associated Legendre functions and their corresponding associated Legendre functions in terms of theta. You see, for meaningful finite solutions of this particular function, we already know that m can take the values of 0, plus, minus 1, etc. We have seen this in the azimuthal solutions. And L can take the values of 0, 1, 2, 3, etc. In fact, there is a particular restriction here that the magnitude of m must be less than equal to the value of L. And based on this, we get a particular table for all possibilities. So here I have the associated Legendre functions for different values of L and M. So we either have L is equal to 0, M is equal to 0, L is equal to 1, M is equal to 0 and 1, L equals 2, M is equal to 0, 1 and 2, L equals 3, M is equal to 0, 1, 2, 3, like that. Okay, you see this? And you can clearly see that there are some oscillations which are arising here. Keep in mind that when theta is equal to 0, so for example here, theta represents 0 here. So we are looking at the value of the function at the north pole, yeah? And when theta equals pi, we are looking at the value of the function at the south pole, yeah? So essentially when we go from the north pole to the south pole, we see the functional variation of this particular solution. Now, because it is represented in a 2D plot, this thing has its own look to it. But what if I plot this in a polar plot? In a polar plot, this would look a little bit different, and that would give you an idea about the sort of origin of the orbital shapes. Here it is, the same table, but the plots, instead of being 2D plots, as I've made before, are now polar plots. So you can think of this basically to be the north pole, this basically to be the south pole, and as theta goes from 0 to pi, you see this kind of a symmetrical functional variation, yeah, for all L is equal to 0, M0, L1, M0, M1, these kinds of cases. And you can see that we end up getting these kinds of lobe kind of structures, yeah. In the lowest case, nothing is happening. You see a constant value. In the L is equal to 1, you end up getting the dumbbell shape that we are familiar with. In the L is equal to 2, you end up getting these cases. L is equal to 3, you end up getting these different kinds of petal lobed kind of structures. Now, of course, these are not the actual orbitals, because to get the actual orbitals, you need to combine all the different parts of the wave function, the radial solution, the azimuthal solution, and the angular solution. However, these are the angular solutions, and they have started developing that familiar pattern that will ultimately give us the actual orbitals of the hydrogen atom. It's quite interesting, isn't it? Usually textbooks do not really go into such details of the visual representation of the solution. I thought that if you would take a look at it, it will become much more interesting. So if we take a look at the solutions that we have obtained, these Legendre functions that we are calling here, what we can further do is we can combine this with the azimuthal solutions to get a nature of the spherical harmonics. But before that, I can also try to normalize it. Okay, since you end up getting a lot of different Legendre function solutions, some of them are orthogonal to one another. That means if you integrate one with the other, you end up getting 0 or a non-zero value. And a detailed nature of that particular condition is essentially given by this particular formula. Now, you know that the Kronecker delta will give you a value of 1 if k and l are equal, and it will give you a value of 0 if k is not equal to l. So for k is equal to l, you will get 1, and for k not equal to l, you will get a 0. So only we are interested in k is equal to l. So if I normalize, okay, I normalize, I have a square, and then I have PLMX. Now, because this is a real function, I don't need to be concerned about the complex conjugate, right? Integrating from -1 to +1, because this is cos theta. So cos theta can take the values of -1 to +1 between 0 and pi. And this is essentially equal to 1. So here I have a square times, I'll just write this particular value, 2l plus m factorial upon 2l plus 1, and l minus m factorial equals 1, which means the normalization constant is 2l plus 1 upon 2 times l minus m factorial upon l plus m factorial root over. Okay, there you have it. So the angular solutions has been finally obtained. Yes. So this is theta with respect to theta. So the normalization constant is going to be the same. I can just write it here as it is, 2l plus 1 upon 2l minus m factorial upon l plus m factorial root over, and you have the Legendre functions, PLM cos theta. Yep, that's it, PLM cos theta. These are the angular solutions to the wave function part, and we have already obtained the azimuthal solutions, right? The azimuthal solutions has already been obtained before. Where is it? Where is it? There you have it. These are the azimuthal solutions. I'll combine both of them to get the spherical harmonic solutions. So there you have it. These are the angular solutions and the azimuthal solutions for you. We have obtained two very important solutions that finally we are going to combine to create this spherical harmonics solutions. The spherical harmonics are very important because the spherical harmonics tell us how the wave function varies with respect to theta or phi when you change the orientation. The radial part only tells us about the variation of the wave function with respect to distance. Spherical harmonics tells us how the wave function varies with respect to theta or phi. So therefore, y, l, m. I'm going to include L and M here in the subscript and the superscript because both the angular solutions and the azimuthal solutions contain these quantum numbers. So now these quantum numbers are going to play a very definite role in deciding the nature of the wave function solutions, right? So they will be included in the subscript and the superscript here. There it is, the spherical harmonic solutions of the hydrogen atom. So we have proved that the spherical harmonics are the solutions of the angular part of the Schrodinger equation. But more than just being part of the eigenfunction solutions of the hydrogen atom, they play an even more crucial role because these spherical harmonics are what we call the eigenfunction solutions of the angular momentum operator. You see, the electron is going around the nucleus and it has an orbital angular momentum. We would be discussing this in more detail in a later video, but I just want to mention in passing here that the angular momentum is associated with two very important operators, the L square operator and the Lz operator, which is the component of the angular momentum along the z-axis. These spherical harmonics are the simultaneous eigenfunction solutions of both these operators. So for L square, you have the quantum number L plus 1 h cross square. And for Lz, you have the quantum number m h cross. These are the eigenvalue equations of the angular momentum operators of an electron in a hydrogen atom. And they are very important because they represent quantization of the angular momentum magnitude and the angular momentum direction, also known as space quantization. You see, the electron in the hydrogen atom cannot have any random magnitude of angular momentum or direction of the angular momentum vector. It is quantized in the context of quantum mechanics. Everything seems to be quantized in quantum mechanics. We'll be discussing this in more detail in the future video, but I just wanted to mention it here in passing. You see, the spherical harmonics are the part of the overall wave function solution, and they are also responsible, therefore, for the overall probability density that we get at the very end. And you must have all seen the typical hydrogen atomic orbital shapes. I want to give you a clue as to why those shapes arise in the first place. You see, those shapes, those peculiar orbital lobe-like structures, they arise due to the nature of these spherical harmonics. Let's take a moment to understand why. You see, the theta solution, which are these Legendre polynomials, we have seen how they look like, right? They simply represent oscillations with respect to theta. So if you go in the spherical coordinate system from north to south, these are the oscillations that you will observe. And the azimuthal solutions, they represent oscillations about the z-axis, yeah? If you go along the equator. In quantum mechanics, everything ultimately comes down to wave nature. Whenever waves are involved, and especially for stationary states, you end up getting stationary waves. Stationary waves has nodal points or nodal lines or nodal surfaces that eventually affect the probability density distribution that we get. How, you may ask? Let's take a look. This is a typical look of a hydrogen atom orbital with the peculiar lobe-like structure that actually arises from the spherical harmonics, which are nothing but standing waves on the surface of a sphere. To understand this, let's first take a look at the spherical coordinate system. The radial solution gives us variation with respect to radius. The angular solutions gives us variation as we go from north to the south pole, and the azimuthal solutions gives us the variation as we walk along the equator. If we somehow plot functional values on the surface of the sphere, then we will get something that looks like this. You see? where the different colors represent different values. The reds represent negative value, the blues represent positive value, and the whites represent zero value, where the eventual wave function will go to zero. Now, this is nothing but a standing wave on the surface of a sphere. We can all visualize a standing wave on the surface of a plane. But what if that plane surface is wrapped around a sphere? This is exactly similar. The only difference is that we have plotted the mathematical value of the function as a color here. But if instead of the color, we represent the value of the function as distance along the radius, then suddenly we get this beautiful shape. These represent the directions of probability densities, where the electron density will eventually have some positive value. And therefore, they are the origin of the peculiar orbital shapes that we see in hydrogen atom. I can in fact go further and give you a list of the different kinds of spherical harmonic functions for different values of the quantum number L is equal to 0, 1, 2, 3 like that. Here I have simply represent the distinct mathematical functions as you can see here. And we can also plot them in a similar manner on the surface of a sphere. So all these cases plotted as a color plot on the surface of a sphere looks something like this. The intensity of the color represents the functional value, and the hue of the color represents phase rotation. The whites, notice, they represent nodal planes where the probability density will eventually go to zero. If we connect this mathematical function value to the radius, then suddenly the shapes look a little different. These are the complex spherical harmonics with the phase rotation included. Now I have to make one thing clear here, is that the orbital shapes that we actually see most of the time commonly in popular culture, they avoid the phase rotations because the phase rotations give you a very peculiar rotation about the z-axis, and that can be done if we convert the complex spherical harmonics to real spherical harmonics. So we simply take linear combinations of these spherical solutions, complex to real spherical harmonics, where if you notice YLM is proportional to PLM cos theta e to the power iota m phi, while YL minus m only affects the azimuthal solution. You end up getting e to the power minus I m phi. These e to the power minus m phi, they represent phase rotations that we saw in the earlier plot and essentially represent nothing but traveling waves, okay, that are effectively rotating about the z-axis, while the Legendre polynomials or the Legendre functions, they represent standing waves that we saw. To get real spherical harmonics, we take linear combinations of both of them. If we take linear combination, then with a little bit of mathematics, it is kind of clear that we will get something like, instead of e to the power iota m phi plus e to the power minus iota m phi, we will just get cos m phi here. And if I take a negative sum, instead of e to the power iota m phi minus e to the power minus iota m phi, we will just get sine m phi here. So now they will represent just standing waves, or I should say standing angular waves, which is a much better representation in terms of the visualization process. And anyways, when we finally do take the probability density, these terms will get cancelled out because of the nature of its function. So it's not going to make much of a difference. The linear combinations will act as a pretty good enough basis for the orbital shapes that we're taking a look at. So these were the original complex spherical harmonics, which when we take linear combinations in this manner, I am showing it to you for every single case, all the various functions involved, the real spherical harmonics would look something like this. The beauty of these shapes is that the phase rotation is now taken care of, and the only thing that is left are standing wave solutions on the surface of a sphere. The reds and the blues, they simply represent these standing wave patterns on the surface of a sphere. It is actually very beautiful because once you understand this, you truly realize the origin of the peculiar hydrogen atom orbitals. Why are the hydrogen orbitals the way they are, with their peculiar lobe-like structures and the dumbbells and the various shapes that we get? Because here the whites represent zero probability, right? Zero value of the function. So if we extend this as the magnitude of the function along the radius, then suddenly we get those peculiar shapes. Now, of course, these are not the exact orbital structures, because to get that, we will have to combine the radial solution. But the radial solution simply represents oscillations along the radial direction. But as far as the orientation is concerned, along the theta and phi direction, that shape arises from the spherical harmonics. And most textbooks don't really go into all these details, but I thought you might find it interesting to see the origin of these kinds of shapes. So yeah, that is very beautiful. Now, let's go back to our calculations and finally complete the problem by solving the radial solutions of the Schrodinger equation. So now we solve the radial part of our equation, which we had separated earlier using separation of variables method from the Schrodinger equation. This is the radial equation, which is essentially an equation with respect to the radial distance only. So to solve it, we have to go through an elaborate mathematical process of substitution, trying to figure out the solution of the differential equations using power series method, etc., etc. It's going to be a little bit lengthy, so we will go slowly, step by step. First, let us substitute the capital R, which is the function of the radial distance, using u upon small r, u being some new variable. If I do this, then of course d capital R upon d small r becomes, in the denominator you have r square, r du upon dr minus u. So this becomes r square d capital R upon d small r equals r du upon dr minus u. First expression that we have. And we can also obtain d upon dr of r square d capital R upon d small r, d upon dr of r du upon dr minus u, which gives us r d2u upon dr2 plus du upon dr minus du upon dr. These two terms gets cancelled out and we are simply left with the first term, which is r d2u upon dr2. Let's substitute back all of this in equation number 2, which will give us 1 upon r is r upon u, and d by dr of r square dr upon dr is r d2u upon dr2 minus 2mr square upon h cross square. This is now potential, which is a function of r, which can now be written as a function of u, because u is related to r, minus total energy equals L plus 1. This is r square upon u d2u upon dr2 minus 2mr square upon h cross square v of u minus e equals L plus 1. Let us take r square upon u to the right hand side, which will give us d2u upon dr2 minus 2m. If I am taking r square upon u to the right hand side, I will have 2mu upon h cross square v of u minus e equals L plus 1 u upon r square. Also, let's rewrite these constants. Minus 2m upon h cross square, I'll multiply so that I'll have minus h cross square upon 2m. On this side, d2u upon dr2 plus v as a function of u times u minus e as a function of, so e is a constant, times u, and minus L plus 1 u upon r square, which will be now multiplied by minus h cross square upon 2m equals 0. All right. So this is minus h cross square upon 2m d2u upon dr2 plus v of u plus you have h cross square upon 2m L plus 1 upon r square. Take u common. This is equal to EU. So this is the now radial part of the Schrodinger equation. All right. So the radial part of the Schrodinger equation is now written in this particular manner, where we know that the potential arises from Coulombic interaction, okay, which we had written earlier as the potential energy expression was minus E square upon 4 pi epsilon naught r. If I substitute this back into our equation, this simply becomes, we have to solve this to essentially obtain a radial solution or radial part of the wave function solution. To do that, we have to make a few more substitutions. Here, we can see that if I take energy to the left-hand side, so here we have energy here, right? E times U. So if I just take E to the left-hand side here, and to the left-hand side here, and here, then I can make another substitution, which is 2m E upon h cross square root over. What is this? Many of you would be familiar with an expression like this. This is nothing but the wave number, which we can specify as k. But the thing is, because we are dealing with the hydrogen atom as a bound state problem, so the energy levels of the hydrogen atom are essentially going to be negative. Yeah, E is going to be negative. So whenever we have a bound system, the energy levels are negative. So therefore, for this to make sense, I will introduce a negative sign here, because if the energy is negative, the negative and the negative will become positive, and the root over of that will be k, which will be a real number. So if I make this substitution, then this essentially becomes 1 upon k square d2u upon dr2. I can do the same thing to the second term. If I do a multiplication of the second term, e square u upon 4 pi epsilon naught r capital E times minus 2me upon h cross square, then minus 2me upon h cross square is nothing but k square. So I'll just put a k square here, minus L plus 1 upon k square r square u equals u. 2 gets cancelled with 2 here. The final expression ends up becoming 1 upon k square d2u upon dr2. This is plus, here you have m e square u upon 2 pi epsilon naught r h cross square k square minus L plus 1 u upon k square r square equals u. Let's make a few more substitutions, okay? Where m e square upon 2 pi epsilon naught h cross k equals rho naught, because these are all constants. M is the mass of the electron, E electronic charge, pi epsilon naught h cross, these are all constants. K here depends on the energy, which is also a constant in the system because of conservation of energy principle. So we can think of this as a constant for a given case. And let us also make the substitution of rho equals kr. So the first term, 1 upon k square d2u upon dr2 can be written as d2u upon d, I should say kr2, which is d2u upon d rho 2. Okay, because I absorb the k here with the r to create the rho. So this is therefore d2u upon d rho 2 plus we have me square upon 2 pi epsilon naught h cross k as rho naught, and what we are left is r and k in the denominator, which is nothing but rho. So therefore this is rho. Okay, and of course there's a u here minus l plus 1 kr is rho square u equals u, which simplifies to this equation d2u upon d rho 2 is equal to, if I take 1 rho naught upon rho plus l plus 1 upon rho square times u. Yeah. So effectively, we have simplified the radial part of the Schrodinger equation into something that looks like this. And this is what we are going to try to analyze here. Keep track of these substitutions because we will have to eventually replace them back to get a solution in terms of R. Now, how do we analyze this differential equation? It's not an easy differential equation to analyze. And first, therefore, we have to look at the asymptotic behavior of this particular differential equation. So now we look at the asymptotic behavior of this differential equation, which means that we try to guess the solution of this differential equation by trying to understand its behavior at very small and very large values of r. So when rho tends to 0, what is the behavior of the solution? When rho tends to infinity, what is the behavior of that solution? We try to guess that, and then we stitch both these two behaviors by some kind of a stitching function. So keep in mind, rho here is directly related to the radius variable, right? R variable. So rho is equal to kr. So what happens under these two conditions? That is what we are trying to analyze. So first condition is, as rho tends to infinity, then equation number 5 simply becomes d2u upon d rho 2 is equal to, the second and the third terms will kind of vanish and you will be left with u. Now, what is the solution of this kind of a differential equation? So many of these solutions, I'm going to write them because these are standard differential equations, but for your satisfaction, I will also provide a simple check for them. The solution of this differential equation is some constant a, e to the power minus rho, plus some constant b, e to the power rho. Again, I want to give you a simple check. You can check that this is actually true. How? Well, if u is indeed like this, u is equal to a e to the power minus rho plus b e to the power rho, then du upon d rho is equal to minus a e to the power minus rho plus b e to the power rho, and further d2u upon d rho 2 is equal to plus a e to the power minus rho plus b e to the power rho, and therefore this is d2u upon d rho 2 is equal to a e to the power minus rho plus b e to the power rho is just u. That's it. We end up getting the original differential equation. Therefore, this solution is a correct behavior for this particular differential equation that we have. Now, As I said, we are interested in looking at the behavior of the solution at small and large values of rho, keeping in mind that rho here is directly proportional to r. Yeah. So can we have a solution that looks like this at large values of r or large values of rho? This second term is not possible because we are all familiar with the fact that in quantum mechanics, the wave function solution need not be just a mathematical solution of the Schrodinger equation. It must also satisfy certain additional properties like normalization and other properties of being single valued, continuous, having single valued and continuous derivatives, etc., etc. These behaviors are important for us because only then we end up getting some meaningful wave function solution at the very end. And if we have a wave function solution that blows up at infinity, then that cannot be normalized. So because this particular term blows up as rho or r tends to infinity, therefore this cannot be allowed from our side as an acceptable solution. So therefore the only acceptable solution that we can use is a e to the power minus rho. Let's keep this as point number, I should say point number 6. Okay, let's say that this is point number 6. Now that we have got an idea about the nature of the solution for very large values of r, let's look at the nature of the solution for very small values of r. For very small values of r, you should get something that looks like d2u upon d rho 2 is equal to l plus 1 upon rho square, l plus 1 upon rho square u. Why? Because for very small values of rho, this is going to become very, very small, extremely small compared to rho here. And as a result, this whole term will be very large. It will be very large compared to the first term or the second term. And as a result, this term will dominate and the left-hand side will be approximately equal to just the third term for very, very small values of rho. In that kind of a scenario, we end up getting this particular differential equation. Again, I'm going to give you a standard solution of this kind of a differential equation with a simple check to see that this is indeed true. Here for this kind of a differential equation, the solution is given as some constant c rho to the power l plus 1 plus some constant d rho to the power minus l. I want to give you a simple check for this also. Let's do a simple check that this is indeed true. So if I have the solution l plus 1 plus d rho to the power minus l. By the way, this is a very simple way of actually checking that this is indeed the solution of a differential equation, because many times what happens, we end up encountering standard differential equations with standard solutions that we just have to borrow from the mathematical subject, right? So du upon d rho is simply equal to l plus 1 c rho to the power l minus l d rho to the power minus l minus 1, and d2u upon d rho 2 is equal to l plus 1 c rho to the power l minus 1 minus l, and minus l minus 1 can be written as minus l plus 1. So plus here d e to the power minus l minus 2. If I take rho square common here, then this term will become, for rho square common in the denominator, this term will simply become l plus 1 c rho to the power l plus 1 plus l plus 1 d rho to the power minus l. So here again l plus 1 can be taken as common. So this becomes d2u upon d rho 2 is equal to l plus 1 is common upon rho square. We are left with c rho to the power l plus 1 plus d rho to the power minus L. So this is nothing but d2u upon d rho 2 is equal to L plus 1 rho square u. There you have it. Using the solution, we have obtained the original differential equation. So therefore, we can use this as an acceptable solution for this particular differential equation. However, again, imposing our behavior of some sort of a meaningful wave function solution, we have to check whether for very small values of rho or small values of r, does this wave function make sense? So for extremely small values of a rho, this is nothing but C e rho to the power L plus 1 plus d upon rho to the power L, right? So for very small values of rho, this will blow up, okay? Blows up as a rho tends to 0. So therefore, we cannot accept this as a solution of the final differential equation, which is the wave function solution. And the only acceptable solution that we can assume to be valid is C rho to the power L plus 1. There you have it. I'm going to name this as equation number 7. Okay, so the radial equation of the Schrodinger equation after many substitutions ended up looking like this, equation number 5. When we analyze the behavior at very large values of r and very small values of r, we got some idea about the nature of the solutions. So if I combine these two behaviors, finally, u rho is equal to, the first behavior is what? A e to the power minus rho. I'm just going to write e to the power minus rho. Forget the constants for now because they will be finally revealed during the normalization process. And C rho to the power L plus 1, I'll just write rho to the power L plus 1. Now this is not exactly the solution, right? This simply gives you a behavior of the solution for different, extremes. It governs the behavior, governs the behavior for very large values of rho, right? Very large values of rho. And this governs the behavior for very small values of rho. And by small values, I mean r. So essentially, it is giving us an idea about the behavior of the radial wave function solution at extremely small distances and the behavior of the radial wave function solution at extremely large distances. So the overall solution needs to incorporate these two behaviors. Perfectly fine, not an issue. The problem is that how do we connect the behavior at extremely small values with the behavior at extremely large values? We don't really know here. So what we are going to do is we are going to multiply this with some other function of rho, let's suppose v, and we will call this as the stitching function. You know, stitching function means we are stitching together the behavior at small values and the large values of r, okay? So now we have at least come closer to a certain kind of a mathematical function that contains the behavior that governs the values at extremely small values of rho, governs the behavior at extremely large values of rho, and the stitching function which combines both of them together to give you an idea about the mid-range behavior, essentially. Now, let's call this as equation number 8 and resubstitute it back into our differential equation, right? The differential equation that we obtained, which was the radial part of the Schrodinger equation after various substitutions with different variables, looked something like this. We have come closer to a certain kind of behavior that the solution will be somewhat like this particular equation number 8. So let's substitute 8 in this particular differential equation, which is this equation number 5, and see what we can do next. Then du upon d rho would look something like, there are three terms, three functions of rho, so minus e to the power minus rho, rho to the power L plus 1, v to the power rho, plus, and here you have L plus 1 e to the power minus rho, rho to the power L V plus e to the power minus rho, rho to the power L plus 1 dv upon d rho. So this is the first order derivative that can be further simplified as e to the power minus rho, and rho to the power L becomes minus rho V and plus L plus 1 V and plus rho dv upon d rho, which can further be simplified as e to the power minus rho, rho to the power L. Here you have L plus 1 minus rho times V plus rho dv upon d rho. To find the second order derivative, I know these are lengthy mathematical expressions, but they are the ones that we have to use to get to the final solution. So this will give us L plus 1 minus rho times V plus rho dv upon d rho, right? And then we have derivative with respect to rho of the first part. This will give us minus e to the power minus rho, rho to the power L plus L e to the power minus rho, rho to the power L minus 1. This is the first term, okay? And then we will have the second term, e to the power minus rho, rho to the power L. Let's take a derivative with respect to this. This will give us L plus 1 minus rho times dv upon d rho and plus v d rho upon d rho, but it will be minus here, okay, minus v. So this is the first term, okay, and plus we have rho d2v upon d rho 2 plus dv upon d rho. Okay, I would suggest that you can also try to solve it on your own in your own notebook so that you can cross-check with the answer that I get at the very end. So here the first expression can be separated into two distinct terms, right? So here I can have the first term can be separated into further because I can have this particular term and I can have, if I take out the second term in the bracket, this particular term, right? Here just remove this part and you're left with this particular term, okay, this particular term, and here you remove this particular term. That's it. Now it looks a little bit more elaborate. So now what we will do is we'll take something common amongst all these three expressions. So here let us take this particular expression e to the power minus rho times rho to the power L as a common term. And if I do that, I will be left with, from here, I will be left with minus L minus 1 plus rho times V. And then we have minus rho dV upon d rho. Fine. And from the next term, I will be left with, because it's e to the power minus rho times rho to the power L, therefore L upon a rho term, and then we have L plus 1 minus rho times V plus L upon rho term times rho dV upon d rho. Fine. I hope you are following these steps. Even though they're lengthy, I'm trying to go step by step. And for the last term, we have plus L plus 1 minus rho dV upon d rho minus V plus rho d2V upon d rho 2 plus dv upon d rho. Okay. This becomes e to the power minus rho, rho to the power L. And within this particular bracket, let me take v common. So if I take v common, I should get minus L minus 1 plus rho. And from here, I should get plus L square upon rho plus L upon rho minus L. And from here, I should get a minus 1. This completes the terms for v. And then if I take dv upon d rho, then I should get the following terms. From here, I should get minus rho. From here, I should get plus L. From here, I should get plus L plus 1 minus rho. And from here, I should get plus 1. And of course, the last term is plus rho d2v upon d rho 2. Okay. This completes the expression. And so further, we can simplify the entire thing as e to the power minus rho, rho to the power L. And we have rho d2v upon d rho 2 plus, so here we get 2L plus 2 minus 2 rho. So plus 2, we can write this as L plus 1 minus rho dv upon d rho. And we have for v, we have, we can write this as minus L and minus 2 and L plus 1 upon rho. So L plus 1 upon rho minus 2 L plus 1 plus rho. So now let us substitute this back into our equation number 5. Substitute in equation number 5 and see what we get. So if we substitute in equation 5, then this equation basically becomes, I think I'll just copy paste to simplify everything. So on the left hand side, we have d2u upon d rho 2, which is this particular expression, right? This particular expression. And the right hand side, we have equals 1 minus rho naught upon rho plus L plus 1 upon rho square. And you have u we have considered to be e to the power minus rho, rho to the power L plus 1, v. E to the power minus rho, rho to the power L plus 1 times v. So here, again, what can we do? So let us take the rho from here out. Okay, so here we have rho to the power L plus 1, right? So let's just write it as rho to the power L, rho, and v. Then we can cancel out these two terms on the left hand side and the right hand side. So this will eventually become, on one hand, we have this particular expression, right? We have this expression. And on the right hand side, we have the expression of rho minus rho naught plus L plus 1 upon rho times v. Okay, so this therefore becomes, it can be rewritten as, so if I take the right hand side and bring it to the left hand side, I can absorb it in the expression for v. So in the expression for v, we have, so v, so if I just absorb it in this expression, after introducing a negative sign, of course, then this becomes right hand side 0, minus, plus, and of course minus here. This will make sure that L plus 1 upon rho gets cancelled. Rho and minus rho gets cancelled. And we are finally left with rho d2v upon d rho 2 plus 2 L plus 1 minus rho dv upon d rho. And here we have rho naught minus 2L plus 1 v equals 0. There you have it. The differential equation number 5 has now been written with the stitching function as this particular equation number 9. To give you a quick recap, we took the radial part of the Schrodinger equation, made a couple of substitutions, wrote the equation in terms of u and rho, right? And then we analyzed the behavior of this particular differential equation at very large values of rho r and small values of rho r, and got a solution that governs for small values of r and large values of r. Combine that with the stitching function v and plugged it back into the equation to get a differential equation of v with respect to rho. Now at this particular point, how do we solve this particular differential equation? And the way we can solve this kind of a differential equation is by the power series solution method, where the solution of the differential equation, which is v now, in terms of v is basically the stitching function that we are unaware of, that we need to combine it to the overall function to get an appropriate behavior for the radial function solution. And with respect to rho, can be written as a power series solution. Yeah, sometimes certain kinds of functions can be written as a infinite series sum. So I'm trying to write this solution as an infinite series sum, and from that particular series we will try to guess the nature of this particular function. So let us assume that this is a summation with the index j going from 0 to infinity, aj rho to the power j. So this will basically look something like a naught rho to the power j is just 1, and you will have plus a1 rho plus a2 rho square plus a3 rho cube, and on, right? This is the stitching function v. What if we take the derivative of v with respect to rho? This will basically give us a1 plus 2a2 rho plus 3a3 rho square plus on. I think here, if I want to write one more term, I will get something like 4a4 rho cube and on, right? Which can be written as a summation of j plus 1 a j plus 1 rho to the power j here, j going from 0 to infinity. You can check that you will get these terms only, right? J plus 1 a j plus 1 rho to the power j. If I take a second order derivative of v with respect to rho, this will give us 2a2 plus 3 into 2 6 a3 rho plus 4 into 3 12 a4 rho square, right? This kind of a series solution, and this will lead to something like a summation over j equals 0 to infinity. You will have something like j plus 1 a j plus 1 rho to the power j minus 1. Again, you can check that this is what we will end up getting: j plus 1 a j plus 1 rho to the power j minus 1. Now what happens if I substitute all of this back into equation number 9? Now then the power series solution will go back into the differential equation, right? So if you substitute above in equation number 9, then the power series solution gives us basically this particular expression, right? This is the expression we have. rho d2v upon dv2, and the rest of the terms are okay. So I'll just plug the power series solution here. This becomes rho d2v upon d rho 2 is summation j plus 1 a j plus 1 rho j minus 1. Now here, of course, the j plus 1 rho and the rho to the power j minus 1, we can simplify that as just write rho j here. That's it. Okay. And the second term will become something like plus 2 L plus 1. Let's separate this. Summation over j plus 1 a j plus 1 rho to the power j minus rho summation over j plus 1 a j plus 1 rho to the power j. So if the rho and the rho gets multiplied, we get j plus 1, and I remove the rho from here. Okay. And the last term is basically plus rho naught minus 2 L plus 1 V is summation over j, summation over a j rho to the power j is equal to 0. There you have it. So the differential equation in terms of the power series can be written in this manner. How can we proceed further is if I make a comparison of the coefficient of the series. Now, of course, it's an infinite series. I don't have to compare all the coefficients of all the series terms. I just have to take a random row to the power j and compare their coefficients to get the recursion formula that I'm interested in. So by comparing the series terms and their coefficients of rho to the power j, we will get something like j plus 1 a j plus 1, and then you have plus 2l plus 1 j plus 1 a j plus 1 minus. Now here, of course, this is the series sum for the rho to the power j plus 1, right? I want to take a step back. So for the term rho to the power j, I will obtain if I substitute j plus 1 with j. So therefore, I should get j, a, j, and the summation here, right? And the summation here. Is that okay? No, there was a two term here. There was this two term, right? Minus rho I should have written. So minus 2. So therefore, here we will end up getting minus 2. And if we, in that particular series, if we compare rho to the power j, then this should give us summation over j, a, j. That's it. Because I have to take a step back because this contains rho to the power j plus 1. Okay. Having done that, the last term that is left with us is rho naught minus 2l plus 1. Again, you have a j rho to the power j is equal to 0. So there you have it. The differential equation now takes this particular form. And this is what gives us the relationship between every single consecutive term in the power series. So what can we do further? I can take, let's suppose a j plus 1 common. This will give us j plus 1, or I should say I can take a j plus 1 times j plus 1 common. This will give us j from the first term. From the second term, I'll have plus 2 L plus 1, right? And that's it. And in the right hand side, I should get something like 2 summation. No, I don't need the summation here. Sorry. Why did I write the summation? There need not be the summation at this point, right? Because we are comparing the coefficients. So therefore, I will just get, so if I take aj common, this will give us minus 2j plus rho naught again, I don't need the rho term here because we are just comparing the coefficients. Rho naught minus 2l plus 1. So finally, we have our recursion relationship for the power series solution, which is aj plus 1 is equal to 2l plus 1 plus j minus rho naught upon j plus 1 j plus 2l plus 2. That's it, times aj. This is the recursion relationship for the power series solution that we considered to be the solution of the differential equation. And now we have to sort of try to understand this recursion formula to get an idea about the detailed nature of the solutions. Let me tell you that this recursion relationship or recursion formula is a standard recursion formula in mathematics, which is for a very specific polynomial known as Laguerre polynomials. So effectively, by comparing this kind of a recursion formula to the known standard recursion formulas that exist for different kinds of functions, we can already get a hint at the nature of the solutions, which are the Laguerre polynomials. But before I go on to the Laguerre polynomials, let us try to get an idea about the terminating nature of this particular power series solution. You see, what happens is that to get a sort of a genuine wave function solution which doesn't blow up, we will have to terminate this kind of a power series at a particular point. Otherwise, the wave function blows up. And that leads to the energy quantization formula. So first, I want to obtain the energy quantization formula for the hydrogen atom by imposing this kind of a termination property to make sense of a meaningful wave function. And then I'll come back to this particular Laguerre polynomials that I mentioned and substitute it back to get the wave function solution. So the recursion formula that we have obtained till now is going to give us an idea about the stitching function, which is part of the radial solution of the Schrodinger equation. However, because this represents the nature of the coefficients of an infinite series sum, at the end of the day, I want to take a look at what happens to the coefficients of this series at very large values of j. All right, so j here simply represents the position of the coefficient. The coefficient starts from j is equal to 0, but what happens to the term when j is equal to 100, 200, 300, or a very large number, so to speak. So if I can make an approximation here, because that is all I'm interested in at this particular moment, a qualitative idea about whether the function at very large values of j blows up or not, because that is an important criteria in quantum mechanics, then the recursion formula will simplify for very large values of j into something like 2, let's suppose, L plus 1 plus j minus rho naught upon j plus 1. And here we have j plus L plus 1 plus L plus 1. Yeah? Okay. What is L here? L is, of course, a quantum number that can take values of 0, 1, 2, 3, like that. For extremely large values of j, I'm going to make an approximation here. So please be with me. For large j, okay? The numerator, of course, is dominated by this particular term, j plus L plus 1. Yeah? You don't have to worry about the rho naught. And in a denominator, you have something like j plus L plus 1 plus L plus 1. Again, at very, very large values of j, I can kind of cancel it out. Yeah, so I can first of all remove rho naught from here because the first term will dominate. And if the first term dominates, I remove the rho naught part. And from here again, these two expressions will also be more or less similar or closer to one another so that we can cancel each other out. And what we are therefore left with is, again, for very large values of j, is aj plus 1 is equal to 2 upon j plus 1 times aj. This is how the consecutive coefficient in the terms in the infinite series expression will relate to one another, which can also be simplified as aj is equal to 2 upon j aj minus 1. Right? Just take a step back. What is aj? This is probably the 100th, 200th, or the 1000th term coefficient, right? And j minus 1 is just one step less than that. What if I go all the way backwards, right? So if I say, okay, it is 2 upon j, but what about aj minus 1? J minus 1 will also have a recursion formula that can be written as 2 upon j minus 1 aj minus 2, right? What about aj minus 2? That would also have a recursion formula that connects to a lower coefficient, which is 2 upon j minus 2 times aj minus 3. What about the aj minus 3 term? That will also have a recursion formula that will connect it to a lower term, which is 2 upon j minus 3 times aj minus 4. And that way we can go all the way down, right, to the lowest term, which is basically a naught, right? A naught is the first term in that particular series. So essentially, the coefficient of the jth term becomes 2 to the power j, and then in the denominator you'll have j factorial a naught, right? Now let's look at the stitching function that we had. So the stitching function, whose solution was written as a power series solution, V, can therefore be now written as V equals summation over aj rho j, right? So V rho equals summation over j is equal to 0 to infinity aj rho to the power j. If I substitute aj here, then we will end up getting 2 to the power j factorial a naught rho to the power j, which is essentially, if I write out all the terms, for j is equal to 0, you will get just a naught, that's 1 here. For j equals 1, you will get 2, denominator is 1, and then you will have rho. And for j equals 2, you'll have 2 square, and here you'll have 2 factorial, and rho to the power 2, and then you'll have 2 cube, 3 factorial, rho cube, and on and on. If you look at this particular series sum, this series sum approximates a very common function that we are aware of. So that can be written as 1 plus 2 rho plus 2 rho square upon 2 factorial plus 2 rho cube upon 3 factorial, and on and on. Can you guess which function this series sum will represent? 1 plus, let's suppose, x plus x square upon 2 factorial plus x cube upon 3 factorial plus on and on. This is nothing but the very common exponential function, right? So this can be written as a naught e to the power 2 rho. Again, keep in mind that I'm only trying to look at the behavior of the solution for very large values of j. So for very large values of j, this function, the stitching function, will approximate this exponential function here, e to the power 2 rho. Now, what if I plug this back into our original solution that we were interested in, which we wrote in terms of u? So equation number 8, u equals e to the power minus rho, rho to the power l plus 1, and v, right? So equation 8 then gives us u equals e to the power minus rho, rho to the power l plus 1, e to the power 2 rho. Here, the first term basically gave us the behavior of the function for very large values of radius. Second term gave us the behavior of the function for very small values of radius. And this is effectively the stitching function that kind of bridges the gap between small and large values of r. Now, if you take a look at this particular function, and by the way, u is related to r. So u is just small r times the radial function, okay? So this essentially is e to the power. So essentially this gets absorbed by this term. You will have rho to the power L plus 1 e to the power rho here. And of course, there is a constant. The constant is a naught. If you want, I can include the constant here. That really isn't going to make any difference. What is interesting is that this particular solution, which is effectively the radial solution times r, there's something wrong with it. I think you can identify it, that it blows up for very large values of r, or it blows up for very large values of rho. You see this? This blows up for very large values of rho. All that effort, you know, writing the radial equation in terms of different variables, making all those substitutions, looking at the asymptotic behavior, looking at the behavior for small r, large r, including a stitching function, creating the necessary differential equation with respect to the new variables, using power series solution, using recursion formula, ultimately led to a particular solution for, of course, large values of the series term that blows up for large radius, which again we cannot accept, right? So what's wrong here? How can we figure out a solution to this? How can we resolve this issue? There is only one way to resolve this issue, and the way to resolve it is if you look back at the stitching function, which was written as a power series solution. See here. Now we assumed that this is an infinite series. You have an infinite series with coefficients, and the coefficients are connected by the recursion formula. The only way to prevent this from happening is if this was not an infinite series, but in fact it was a finite series. That means for some reason the series terminates after a certain number of terms. If that happens, then we can avoid this particular behavior that we do not want in a quantum mechanical system anyways. The wave function should be normalizable. It cannot blow up. If it does blow up, then we do not get meaningful information from it. So we are therefore imposing that instead of a infinite series sum, we get a finite series sum where the series terminates at a maximum value of j. Okay, you getting what I'm saying? The series must terminate at some value of j. That is the only way to resolve this. The power series must terminate at some value of j, or we can call j max. If that happens, then if we take a look at the recursion formula, again, when is that possible? That is possible if after a certain term aj, the next term aj plus 1 comes out to be 0 for whatever reason, right? So we have a number of terms, a0, a1, a2, a3 like that. You reach aj, and then the next term aj plus 1 comes out to be 0. What could be the condition for this? The condition for this is extremely simple if this denominator somehow turns out to be 0. If this denominator turns out to be 0, the next coefficient term is 0. And because the next coefficient term is 0, the one next to it is 0. The one next to that is 0. Again and again and again. Effectively, the series has terminated now. And we can avoid this blowing up behavior. So for this particular condition, for let's suppose j equals j max being that particular value of the index where this series coefficient term vanishes. This leads to 2L plus 1 plus J max minus rho naught equals 0. This leads to 2L plus 1 plus J max equals rho naught. Now I'm going to call this particular term L plus 1 plus J max equals something called N, right? J is an integer, L is an integer, 1 is an integer. So here we have some integer N, and for this particular integer N, the entire series terminates, so that we end up getting some sort of a relationship that 2n equals rho naught. What is the value of n here? We will figure it out. But right now we just know that n is some integer. Of course, the lowest possible value of L is 0. The lowest possible value of J is 0. And then you have 1. So therefore, the lowest possible value of n is 1. So it is probably 1, 2, 3, something like this. Okay. So let's go back to our calculations, where we assumed rho naught as something that looks like, where is it? Yep, here it is. This particular expression, you see, rho naught consists of a large number of constants. So the imposition that the series must terminate led to this particular quantum number n, which is related to the nature of the termination of the particular series, which introduces a distinct quantization behavior. And I'm just mentioning it here, but this will be known as the principal quantum number. Why principal quantum number? Because as I am going to show it to you, it's going to be related to energy quantization. Okay, so here we have it. The 2n value is equal to rho naught. So rho naught therefore ends up becoming this. Okay, this is the expression. And now if we are interested in finding out the energy term, what is the energy term? Energy is what? If you forgot, let's go back to our calculations, because we made a few substitutions earlier where we assumed that, energy is basically given by this expression. Okay, so let's rewrite this expression again. Minus 2m E upon h cross square equals k square. So minus 2m E upon h cross square equals k square. So energy is basically equal to minus h cross square k square upon 2m. From here, we can obtain the necessary relationship. So let me write down this in terms of k. So k is basically equal to m e square upon 4 pi epsilon naught h cross n. Okay, let's use this here. If I use this here, this will give us minus h cross square upon 2m times m square e to the power 4 upon 16 pi square epsilon naught square h cross square n squared. Here h cross square gets cancelled, m gets cancelled, and we are left with an energy formula. E equals minus m e to the power 4 upon 32 pi square epsilon naught square n squared. When I made the substitution of rho naught, okay, let's take a look again. It's a small typo. I will just correct it here. If you take a look at this particular expression, rho naught equals m e square upon 2 pi epsilon naught h cross squared. Okay, so if I make that correction here, there should be an h cross square term. H cross square term, yep, here. h cross square, h cross square, and this should be h cross to the power 4. Yep, I think now it's perfectly fine. So therefore I will have a h cross square term remaining here in this particular expression. So yeah, this is the final expression for the energy eigenvalues. I'm going to mention it as En because it depends on n, right? And n being an integer will highly affect the values that we actually end up getting. If you look at the values of all the other sort of variables, m is the mass of the electron, E is the electronic charge, pi is pi, epsilon naught is permittivity of free space, h cross square is Planck constant upon 2 pi. These are all constants. You can plug them into these particular values if you want, and you can try to check what value you eventually end up getting. Because it's energy, you end up getting minus 13.6 in terms of electron volt. So you can convert joules to electron volts also, upon n square electron volt. There you have it. These are the energy eigenvalues that we have finally obtained for the hydrogen atom. So in the hydrogen atom, just like any other kind of a quantum mechanical bound potential, we end up getting energy levels which are quantized. That means the particle cannot have a continuous distribution of energies. In fact, if an electron is in the hydrogen atom bound state, it will have only certain discrete levels which is allowed by the energy values. So if I do draw an energy level diagram, then for an electron in the hydrogen atom system, the energy level diagram can only be occupied at very specific values. Okay, so we can think of, like, let's suppose n equals 1. N equals 1 will correspond to minus 13.6 electron volt. Okay, we can think of n equals 2, which will correspond to minus 13.6 upon 2 square electron volt. We can think of n equals 3, which will correspond to minus 13.6 upon 3 square electron volt, and on, right? So there it is. These are the allowed energy levels for the electron in a hydrogen atom. The electron cannot have any random energy value. It must only have an energy value which is allowed by this particular equation. This is something that is characteristic to the nature of quantum mechanics as a subject itself. All kinds of bound potentials we end up seeing have discrete energy level diagrams. This is peculiar to the hydrogen atom. But before I elaborate more on this, let us look at the final solution, which is the radial solution that we are trying to obtain. And we'll come back to this energy level diagram and we will see how the principal quantum number n and the other quantum numbers are related to one another. So now it's time to wrap up our calculations. Let us look back at some of our substitutions. First, k equals me square upon 4 pi epsilon naught h cross square can be simplified to me square upon 4 pi epsilon naught h cross square times 1 upon n. Here, 4 pi epsilon naught h cross square upon me square. Now this is entirely a constant. 4 pi epsilon naught h cross me. These are all constants. We will call it as a. And if I plug in the value of all these constants, it turns out to be 0.529 angstroms, with a unit of distance. Okay. As it turns out, this is nothing but the Bohr radius. Okay, so later on we will find if you're interested in further calculations, that the most probable distance for the ground state turns out to be exactly this particular value. But for the time being, I'll just keep it here as the constant a. So this becomes 1 upon an. Now, some of the earlier substitutions, I'm going to bring it back now, where we chose earlier that rho equals, what is rho equal? Rho equals kr. This is one substitution that I'm going to use. And another is r is equal to u upon r, where u is something that we have already solved using the recursion formula for this particular expression. So let's take all of them together to see finally what we can get. Okay, so this is u, and this will help us in constructing at least the ground state solution. Okay, so also rho equals kr, and r is equal to u upon r, where u is basically what we have solved in this particular manner. So therefore, finally, r can now be written as r, which is a function of r, is written as u upon r. So we have 1 upon r e to the power minus rho, rho to the power l plus 1, and then you have v rho here, okay, which can further be simplified. If I write this rho as a substituted value here, then k is nothing but 1 upon n. So you have r upon a n. If I substitute this here, this becomes capital R is equal to 1 upon r e to the power minus r upon a n, and then you have r upon a n to the power l plus 1, and then of course you have v as a function of r upon a n. Okay, so now we have a little bit of a more simpler look or finalized look to the radial solutions. So without getting an idea about the general nature of the power series solution, we can still obtain the first couple of radial solutions. Yeah, because the polynomial can give us at least a couple of the radial solutions. So let us at least try to obtain the ground state solution so that we know that we are on the right track. Okay, so what is V here? V here is the power series solution given by this particular recursion formula. Yeah, so let's bring the recursion formula here. We'll be using this, and of course the power series solution is something that we have substituted earlier as this. I'm going back to my, going back to my calculations because I want to just give you the chance to look back what we did earlier. So now let us see if we have a terminating power series solution, what is the ground state solution that we can obtain? Okay, now when does the power series solution terminate? It terminates at, here we have again mentioned that the termination happens for L plus 1 plus J max equals N. All right. So L plus 1 plus J max equals 1. L plus 1 plus J max equals N. All right. Now, the lowest possible value of L is, of course, 0. Lowest possible value of N is, of course, 1, because we would not have a meaningful energy eigenvalue for N is equal to 0. So N is 1 is the lowest possible value. That means the lowest possible value for J max is equal to 1. That means the entire series must terminate beyond this particular point. Okay, that means A1 must be equal to 0, A2, A3, A4, everything must be 0. Terminates after this. Okay, so we are just trying to obtain the ground state solution first. Okay, I'm just going to give you a feel of obtaining the solutions from this power series solution one by one before giving you the general expression. So if this is how it is, then of course the stitching function v rho is nothing but a constant a naught here. Okay, there's also a reason that I've chosen this particular constant as a. In certain textbooks, they write this as a naught, is because I wanted to distinguish it with our coefficients a naught that I have taken. So therefore, the radial solution for the ground state R, okay, for n is equal to 1 and L is equal to 0 comes out to be 1 upon R e to the power minus r upon n is equal to 1. So you have just a, and you have r upon a. L is equal to 0, so just power is 1. And here instead of v, we just get a coefficient a naught. There you have it. We have some kind of a expression where the ground state radial solution turns out to be a naught 1 upon a e to the power minus r upon a. Okay, a here represents the Bohr radius, so we'll keep that separate. A naught is a coefficient, which is a constant, and its value can be obtained by the process of normalization. Okay, so we can normalize this thing to get an idea about what a naught is. So how do you normalize it? If we normalize the radial solution, we have r mod square, but because we are dealing with a 3D problem, essentially we are dealing with some sort of a spherical volume, and we want to find out the probability density at a radial distance. So we will be taking a shell element. So because of that reason, I will have to integrate with respect to r square dr from 0 to infinity equals 1. Okay, if I do this, then this simply becomes a naught square. But because this is a real function, so I'll just write a naught square here. And here you have times 1 upon a square integration of e to the power minus 2r a times r square dr from 0 to infinity. This here is a standard integral. Many of you may be aware of it. So if I have an integral of this form, x square upon e to the power minus cx from 0 to infinity dx, it is nothing but 2 upon c cube. So using this, our terms become 1 upon a square, and here we have times 2 upon a cube equals 1. So we are left with a naught square is equal to 4 upon a. So the normalization constant a naught is equal to 2 upon root a. Thus, substituting it back, we have finally r 1 0 is simply equal to a naught is 2 upon, this is 2 upon root a, right? So 2 upon root a times 1 upon a times r upon minus a, sorry, e upon r upon a. So e to the power minus r upon a. So this is basically equal to 2 to the power a root a e to the power minus r upon a. This is the ground state radial solution for the hydrogen atom. If I combine this with the spherical harmonics, then I should get our final wave function solution. So let's go back to our section of spherical harmonics, and let's take a look at the spherical harmonics that we have obtained. For L is equal to 0, the spherical harmonics is root over 1 upon 4 pi. Yeah. So y00 is root over 1 upon 4 pi. If I combine this here, I end up getting y00 theta phi equals 1 upon root over 4 pi. So the ground state wave function is psi n is equal to 1, L is equal to 0, m is equal to 0 with respect to r theta phi is equal to the radial solution 2 upon a root a e to the power minus r upon a times the spherical harmonics, which is 1 upon root 4 pi. So this here 2 and the root 4 gets cancelled. We are left with 1 upon root pi a cube e to the power minus r upon a. There you have it. After so much effort, we have finally obtained the ground state wave function solution for the hydrogen atom in terms of the radial and the angular variables. Of course, the ground state wave function solution does not depend on theta and phi, which means that it's going to be spherically symmetric, which indeed it actually is. So we call this 1s, 1 for n is equal to 1, s for l is equal to 0 orbital. I'm going to give you a visualization of these orbitals in just a moment. But I want you to notice that we obtain this solution from the power series solution by terminating the terms after the first term, right? In this manner, we can also look at all the functions of the radial solution by terminating this power series after the second term, after the third term, after the fourth term, the fifth term, and on and on. That way, we can actually obtain a detailed functional value for our solutions. However, the recursion formula that we have achieved can also give us a much more better idea about the nature of the function involved, because in mathematics, this recursion formula is associated with a certain class of polynomials known as associated Laguerre polynomials. So in physics and mathematics, the power series in which the consecutive terms are related by this kind of a recursion formula corresponds to a class of functions which can be represented by what is known as associated Laguerre polynomials. So let me give you the expression corresponding to that. So the associated Laguerre polynomials are written by the expression of L. I want to give you a list of the first couple of Laguerre polynomials. So on the right hand side, we have the first 5 Laguerre polynomials based on this definition. So I am using the definition based on the Griffiths convention, the one given in the textbook of quantum mechanics by Griffiths. And on the left hand side, we have the finalized associated Laguerre polynomials, as you can see here. Okay, so this will give us an idea what the general nature of the radial solutions will look like, because at the end of the day, these are going to get multiplied to the radial solutions and their corresponding wave function parts. So these are the Laguerre polynomials. The left hand side table gives us the associated Laguerre polynomials. The right hand side just gives us the Laguerre polynomials according to the formula I just mentioned. If you look at the graphical representation, which I have included here in this picture, you can see that with increasing order of the Laguerre polynomials, you can see a slight increase in the nature of the oscillations. So for L0, all the terms have some kind of a constant value. For L1, the graph will intersect only once, giving you one single root or a nodal point. For L2, you have 2 nodal points. L3, you have 3 nodal points, and on, thus giving us a hint about the nature of the solutions. So let us now include this solution into our general expression for the radial solution. Yeah, so I'll copy this expression for the radial solution, and let us see what we get. So finally, yeah, I think we have earned the right to say the word finally now, because we are very close, pretty close to the final solutions. These are the radial solutions. Yep. And here we have 1 upon r e to the power minus rho. What is rho? It is r upon an, as we just derived a couple of moments earlier. So you have r upon an to the power L plus 1. And keep in mind that the function v is actually the Laguerre polynomial with the subscript n minus L minus 1 and 2L plus 1 2 times rho. All right. So if I include this, then instead of the stitching function v, we will have a different expression, right? So let me include this here, the Laguerre polynomial of 2 row, where 2 row is given in this manner. So instead of 2 row, I'm going to write this as a 2 times rho, which is 2 times r upon a naught or an. So we can further simplify it. Let us see if we can further simplify it. So we have 1 upon r, and here this particular term that can be simplified as r times an times r upon an to the power l, and then the exponential term e to the power minus r upon an, and the Laguerre polynomial n minus l minus 1 2l plus 1 of 2r upon an. A is a constant, n is a quantum number. I hope you still remember this. It's easy to get lost in so many different terms, yeah. So if I simplify this, here r gets cancelled, yep, and we have, what I'm going to do is I'm going to do some substitution here. So let's say that this is 1 upon an, and for the sake of a little bit of a uniformity, I will include 1 upon 2 to the power l term here. So here I can write 2r upon an to the power l e to the power minus r upon an, and the Laguerre polynomial n minus l minus 1 2l plus 1 of 2r upon an. Okay. Now, before we combine this with the to get the final wave function solution, I would like to normalize it. Okay. So if we normalize it, then this can this entire function can be multiplied with some sort of a normalization constant, right? Let us multiply with a normalization constant a. Okay. So if we do that, then the integration of r. Now, of course, here the most general way of writing r is to include n, l in the subscript, because r, after all, depends upon n quantum number and l quantum number. So r, n, l mod square, because we are integrating the radial wave function to get an idea about the probability along the radial direction. So we have to take a small shell volume, which will contribute a term of r square dr from 0 to infinity, giving you an expression equal to 1. So this therefore ends up becoming, so you have a square, all right, and you have 1 upon an square, all right, you have 1 upon 2 to the power 2l, all right, and then you have inside the integration 2r upon an 2l e to the power minus 2r upon an, and of course the r square term is here, and the Laguerre polynomial n minus l minus 1 2l plus 1 of 2r upon an whole square dr is equal to 1. Here we can do a couple of substitutions to simplify this. So the substitutions I'm going to do is 2r upon an equals u. Therefore, r is equal to u an upon 2, and dr is equal to an upon 2 du. So this becomes a square times 1 upon an square times 1 upon 2 to the power 2l integrate 2r upon an is u to the power 2l times e to the power minus 2r upon an is minus u times r is u an upon 2 square ln minus l minus 1 2l plus 1 of, again, u here 2r upon an is u whole square times an upon 2 du equals 1, which further simplifies to a square times 1 upon an square times 1 upon 2 to the power 2l times, here you have an upon 2 square, right, this term, times an by 2, an by 2. I will simplify this, all of this, and the expression that you are left with times u to the power 2l times e to the power minus u. And because you have a u square term, I can include that in the first term itself. So u to the power 2l plus 2 times e to the power minus u l n minus l minus 1 2l plus 1 of u whole square du equals 1. Now what we can do here is we can include a certain orthogonality condition associated with Laguerre polynomials. So this is an identity that can be derived from the properties of Laguerre polynomials. Now this is not the standard expression for the orthogonality condition. It can be arrived at from the standard orthogonality condition by making some substitutions. I am going to leave that proof to you guys. It's not really that necessary because that's a detailed separate mathematical problem. If you do a quick search, you will find that this expression is indeed valid. I am following the expressions which are used in the textbook of Griffiths quantum mechanics. So using this property of Laguerre polynomials, I can substitute back here to solve this particular problem of normalization. If I make a comparison, here it is clear that 2l plus 1 is equal to k based on the expressions. N minus L minus 1 is equal to M. So if I substitute this back into our expression, this expression simply becomes a squared. And here we have an squared and an squared, it gets cancelled. And we are left with 2 to the power 2l plus 2, right? So this gets cancelled, an upon 2 square and an square, not the 2 term of course, just the an square term here, okay? And we are left with again an upon 2. And in this integration, if I make the necessary substitutions, we can write m is equal to n minus l minus 1 plus k is equal to 2l plus 1 factorial cube upon m, which is n minus l minus 1 factorial times twice of m, so it is 2n minus 2l minus 2 plus k, so k is 2l plus 1 and plus 1, okay? So this is equal to 1. So now this equation takes the shape of something that will look in this manner. But before that, let me cancel out some of the terms here. 2l and 2l gets cancelled, and minus 2n plus 1 gets cancelled. So we are left with a square is equal to 2 to the power 2l plus 2 times 2 upon an times n minus l minus 1 factorial upon here. So minus 1 and plus 1 gets cancelled. You are left with n minus n plus l factorial cube times here the 2 and this 2 gets cancelled. And if I take square root of the entire expression, then I end up getting the normalization constant. So this is our normalization constant that can be obtained using the orthogonality condition for Laguerre polynomials that I have written here in this particular manner. And if I substitute this back into our equation, which is basically the radial solution equation, which is this one, then I think I should get an appropriate term for the final solution. Okay, so finally we have the radial solution, which is R and L function of R. If I multiply with A is nothing but this particular expression to the power half, right? I'll just multiply it here, and this expression becomes, so here we have, if I put everything inside the root over, let's suppose, then this becomes 1 upon an square times 1 upon 2 to the power 2l times 2 to the power 2l plus 2 times 1 upon n times n minus l minus 1 factorial upon n plus l factorial to the power cube to the power whole half, right? And then I write down the functions, which is 2r upon an to the power l e to the power minus r upon an times the Laguerre polynomials 2r upon an. Okay, so here how can we simplify it further? 2 to the power 2l gets cancelled, and there is this particular term here, right, that I did not include anywhere, so I need to include this. So 1 upon an square, and then this is also 1 upon an, so this is essentially going to become cube. Okay, let's take a quick look again that all the expressions are in order. This finally becomes r and l of r is equal to, so here we have this 2 term, 2 square. If I include another 2 term in the denominator here, then in the numerator I will basically have 8, so which can be written as 2 upon an cube, right? All right, so I'll incorporate a 2 in the denominator, and then I basically have n minus l minus 1 a factorial upon, so I had a 2 here, so therefore it is 2n times n plus l factorial cube, and I'll have to put a square root term over here, and then the functions begin 2r upon an, or you can write na. Okay, n is the quantum number, so let's write that first, na, and here also you have na to the power l e to the power minus r upon na Laguerre polynomials n minus l minus 1 2l plus 1 2r upon na. That is it. This is the radial solution, guys. This is the radial solution. Yeah, so this is the radial part of the wave function solution. There you have it. It looks complicated because of the normalization constant involved. It's a little bit of complicated normalization constant that requires the values of the quantum numbers n and l, but effectively it contains this particular function r to the power l, right? It contains this function e to the power minus r something, and it contains these Laguerre polynomials. Together, they will give us the radial solution of the wave function solution of the hydrogen atom. So let's first take a look at the radial solutions, and then we will combine the radial solutions with the spherical harmonics to get the overall wave function solutions. So finally, the time has come for us to combine everything that we have obtained together to create the wave function solutions and get understanding of the probability density distributions for a hydrogen atom. So let's start with the radial solutions. The radial solutions that we have obtained here is essentially this particular expression. You can ignore the normalization constant because that only gives us an idea about the amplitude, and look closely at the functions involved. What is the role that these functions are playing? The functions, if I represent for different values of n, essentially looks like this. So the first case, this is n is equal to 1, L is equal to 0. The second n is equal to 2, L is equal to 0. Third here, n is equal to 2, L is equal to 1. And then n is equal to 3, L is equal to 0, etc. These are the plots that I have made for you. And if you notice, with increasing value of n, you end up getting a certain oscillatory behavior. Of course, I've tried to create all these plots with the same constant scaling. That's why if you look at the scale in the x-axis or the radial axis, the scaling is constant throughout the plot so as to give you a much better perspective of how the orbitals or how the probability densities look like. Some few key takeaways that, or we should say important points that I would like to mention here are as follows. If you look at our expression, then as r tends to 0, then this particular expression r to the power L is going to dominate, right? If r to the power L dominates, then for L is equal to 0 values, which we will call as S state, then r to the power, or I should say r to the power, essentially goes to some kind of a constant value here. Okay, so therefore you see for all L is equal to 0 cases, this one, and this one, at radius 0, you end up getting some constant amplitude. Okay, this is an important takeaway here. But when L is greater than 0, then as r tends to 0, the radial solution goes to 0. So as you can see here, for our L is equal to 1, the amplitude is 0 at 0 radius. This is an important point. Now, if you look at for very large values of the radius, this function is going to dominate, the exponentially decaying function. So as r tends to infinity, the r expression is dominated by e to the power minus r upon na, which basically goes to 0 for all cases, right? This goes to 0 for all cases. So as you can see here, the function goes to 0, 0, 0, 0. And this is important because ultimately we want the wave function to go to 0 as we go very, very far away from the nucleus. This ensures normalizability and also a meaningful probability distribution for this kind of a Coulombic potential. So for r is equal to 0 and r is equal to infinity, this is the behavior that we see. Now, if you look at the oscillatory behavior of the radial function, right, that oscillatory behavior is introduced by the Laguerre polynomials. With increasing value of n and L, the Laguerre polynomials basically have this many number of roots, n minus L minus 1. So we will get this many value of nodes in this particular distribution. Let's name these points 1, 2, 3. The R function has n minus L minus 1 nodes as the Laguerre polynomial n minus L minus 1 and the superscript is 2L plus 1 is a polynomial of degree, is a polynomial of degree n minus L minus 1. So if you notice here, n is 1, L is 0 minus 1. There are 0 nodal points here, right? So there are 0 intersections with the horizontal axis. If you notice here, 2 minus 0 minus 1, there is one particular point where you see this kind of a intersection with the horizontal axis. Here you have 2 minus 1 minus 1. Here there are no nodal points. Here you have 3 minus 0 minus 0 minus 1. You end up seeing 2 of these points. Okay, so what are these points in which the function effectively sort of crosses the horizontal axis? These will ultimately represent 0 probability points. And because we are talking about the radial direction and the atom is effectively a spherical atom, along the radial direction, these points are essentially nodal surfaces. Okay, these are nodal surfaces. In the third plot, we can see these nodal surfaces as white lines here. We see these nodal surfaces as white lines. Okay, these white lines refer to the nodal surfaces around the hydrogen atom in which the probability of the electron being found is absolutely 0. Okay, and therefore the radial solutions effectively end up creating this kind of a shell-like structure with increasing value of n. Okay, so as the n increases, you end up getting more and more, not exactly, but effectively more and more shells of probability clouds. Now, coming to probability clouds, the second row here represents probability. Okay, now if I want to calculate radial probability, the radial probability is basically given by R is essentially R and L mod square dr, or I should say R square dr, because effectively we're looking at the probability of a given shell. And when I do this, I'm essentially not only taking the mod square of the radial function, but also multiplying with R square. What this does is it ends up giving me these plots that I have demonstrated here. In these plots, you can see that we multiply the wave function or the radial solution with R square and plot it accordingly, then we end up getting these kinds of probability density distributions. This is the purest form of the radial probability density distributions. For the smallest wave function or the smallest state, 1s, you end up getting this kind of a probability density. That means as you go along the radius outwards, the probability of the particle being found increases sharply, reaches a maximum, and as you go further away, it decreases. For the state 2s, as you go away from the radius, or as you go away from the nucleus, the probability increases once, decreases, goes to 0, again increases, and eventually goes to 0, thereby creating this kind of a nodal surface where the probability of the particle being found is 0. For here we have 2p, we just get one sort of a shell-like structure. Of course, this is not the final orbital, because that would need that we include the spherical harmonics, but this is just the radial probability distribution. For 3s, we have these kind of 3 shells. Okay, so when I plot this radial probability distribution plot from a 2D plot to something that looks like this. In a plane, I've taken a quadrant. So here you can see, so for 1s, you see this shell of probability density cloud. For 2s, you see these 2 shells of probability density cloud. For 2p, you see this single shell. Of course, this needs to be multiplied with the orbitals. For 3s, you see these 3 shells of probability density clouds. So effectively, the contribution of the radial solution is to introduce these kinds of oscillatory function along the radial direction that effectively ends up creating these probability shells or probability cloud shells as we go higher up in different values of the quantum number. These are effectively the result of the Coulomb potential, the nature of the Coulomb potential. And as we go higher up in the principal quantum number, you can see the sizes also keep on increasing. So if you calculate the expectation value, an expression that is proportional to n square. So as you go higher up in energy, because n is related to energy, then you end up getting bigger and bigger regions in which the hydrogen probability density distribution exists. So now the question is, how can we combine these sort of plots that I've made in 2D with that of the spherical harmonics to eventually get the ultimate orbital shapes and structures? So the final wave function solutions are very much decided by the quantum numbers that we have discovered along the way. Okay, the quantum numbers that we have discovered along the way are, number one, the principal quantum number, which we call as n, the angular quantum number, or I should say the angular momentum quantum number, which we call as L, and the magnetic quantum number, which we call as M. So the distinct values of these quantum numbers are decided by the nature of the solutions that we have got. So for example, if we go back to our radial solution, we had to terminate the power series solution, remember? And if we terminate the power series solution in this manner, then the lowest value of n that is possible is clearly n is equal to 1 from here, right? We can go from n is equal to 1 to 2 to 3 to 4 and on up to theoretically infinity. And if we look at the value of L, of course, L arises whenever we try to solve the angular solution. And when we solve the angular solution, we got the Legendre polynomials, remember? The Legendre polynomials have the order starting from 0. So L can have 0 value. The smallest value for L is, of course, 0. And again, if we combine that information with the value of n, the L starts from 0, 1, 2, like that. But because of this particular expression, it can only go up to n minus 1. Yeah, L is equal to n minus 1. That's the smallest value which is possible. M, of course, again, comes from our Legendre polynomials that we discovered in the sort of spherical harmonic solutions. Here, M can have positive and negative values. So L therefore can take the values of minus L to plus L, right? From minus L up to plus L. So therefore, the quantum numbers that we have obtained, the principal quantum number can take the values of 1, 2, 3, on and on. It decides the energy eigenvalues, as we discussed earlier, minus 13.6 upon n squared electron volt. So as the energy of the hydrogen atom is increasing, the energy eigenvalues will shift in this particular manner. We get distinct energy levels, and the energy is purely determined by the principal quantum number. The angular momentum quantum number and the magnetic quantum number, as I mentioned earlier, is associated with the magnitude quantization and the direction quantization of the orbital angular momentum of the electron. Okay, even though the electron has a probability density cloud around the hydrogen atom, we don't really have a revolution type scenario going on in the quantum mechanical picture. It still has an orbital angular momentum, which can be decided or figured out from the quantum numbers L and M, which can take the values of 0, 1, 2, up to n minus 1. And M can take the values of minus L plus 1, up to L minus 1 and L. Okay, now because of convention, the L is equal to 0 corresponds to s orbitals, L is equal to 1 corresponds to p orbitals, L is equal to 2 corresponds to d orbitals, and on and on. So if we draw a picture for n is equal to 1, you can have L values, which is 0, right? And you can have M values, which is 0. So therefore, the wave function corresponding to this will be psi 1, 0, 0, right? But if n is equal to 2, you can have L value 0 as well as 1. If L is 0, M is 0. And if L is 1, M is minus 1, 0, and plus 1. So you can have here psi 2, 0, 0. And here you can have psi 2, 0, or I should say 2, 1, minus 1, right? 2, 1, minus 1, psi 2, 1, 0, and psi 2, 1, 1. For n is equal to 3, you will have L is equal to 0, 1, and 2. And the corresponding M values are something like this. So again, you can get the wave functions according to this particular thing. So for every L value, okay, so if we want to calculate the degeneracy, because these all result in distinct wave function solutions that have the same energy level, because the energy level is just decided by the principal quantum number. So if we look at the degeneracy here, then for every value of L, there are 2L plus 1 values of M. So for every value of L, there are 2L plus 1 states. And for every value of N, you end up getting N squared. So that means for every value of principal quantum number, you get N squared distinct energy eigenstate solutions for the hydrogen atom. Now, this picture does not include the spin quantum number. We also have something called the spin quantum number, but because the spin quantum number is not predicted by the non-relativistic Schrödinger's equation, I'm not going to include it here. Spin quantum number is something that has to do with the spin angular momentum of the electron. Whether or not it's part of the hydrogen atom, it doesn't matter. It's an intrinsic quantity that subatomic particles have and electrons have. It's an intrinsic angular momentum. This is something that is predicted by the relativistic version of the Schrödinger equation, not the non-relativistic version. So right now we are in the sort of the domain of non-relativistic Schrödinger equations quantum mechanics, where the spin quantum number is not yet included. So if we do include the spin quantum number, because electrons can have two spins, spin up and spin down, the degeneracy will of course become 2n squared. I'll keep it aside because we are right now only looking at the energy eigenstates. So this many number of energy eigenstates will be there. So let us combine our final expressions of the spherical harmonics, right, that we had obtained earlier, and the radial solutions that we have just now obtained to get the final description of the wave function solutions. So the spherical harmonics are these, right? And the radial solutions are these. Okay, so we end up getting extremely complicated looking expressions. But I have to note here that hydrogen atom is one of those problems that can be analytically solved using the Schrödinger equation. Okay, this is one of those simpler systems that can be solved by the Schrödinger equation. So this is the radial solution. And these are the spherical harmonics or the spherical solutions. Okay. When you combine them together, you get the overall eigenfunction solution. Okay, so let's combine them together and see what we get. So combine to get the wave function solution or the eigenfunction solution, which is the space dependent part of the wave function solution, is equal to, so all these complicated terms, they are nothing but the normalization constant at the end. And we are left with the function, Legendre polynomial, and azimuthal solutions here. Okay. All right. There you have it. We have solved the wave function solutions for a hydrogen atom system. So if you look at the different functions involved here, then this particular expression, the exponential decay, ensures normalizability as we go along the radial direction. This particular function r to the power L essentially kind of suppresses the wave function solution as we go towards the origin, towards the nucleus. This particular function, the associated Laguerre polynomials, gives us oscillations along the radial direction. This particular function, the Legendre polynomials, gives us oscillations as we go from north to south along the angular distance. And this particular function, the azimuthal solutions, gives us oscillations as we go along the equator. Together, the spherical harmonics essentially give us standing wave patterns on the surface of a unit sphere. These standing wave patterns that have their own nodal surfaces effectively kinds of affects the overall wave function in the sense that it gives direction to which particular direction the electron cloud is supposed to be, because the radial solutions basically tell us how far the electron is going to be from the nucleus, and the angular solutions, the spherical harmonics, tell us in which direction the electron is going to be. Okay, so do you remember the spherical harmonics that we saw earlier? So here it is. These are the real spherical harmonics that I showed you earlier when we were talking about the angular solutions. Okay. Now the angular solutions effectively create standing wave patterns on the surface of a unit sphere. And if you look at the functional value and express that functional value as magnitude along the radius or magnitude squared along the radius, then you end up getting these orbital shapes or these kinds of lobe-like structures. Okay, now there is something very interesting here that we can combine with our overall solution, which has to do with the nodal structures. Okay, if you look at the nodal structures, it will give you a much more intuitive idea about the orbital shapes. If you look at the nodal structures, when we looked at the radial solution, I told you that in the radial solutions, there are n minus L minus 1 nodal surfaces, right? Because of, the radial solutions, there are n minus L minus 1 nodal surfaces. But if you look at the spherical harmonics, there are effectively L number of nodal planes, which we can combine to create the total number of nodal surfaces in the final expression, plus L. So this is introduced by the radial solution, and this is introduced by the spherical harmonics. So there are total n minus 1 number of nodal surfaces that you are going to get. So here let's take a look at some distinct orbitals compared to L is equal to Z1 and L is equal to 2. Okay, so for L is equal to 1, you end up getting the p orbitals, the various p orbitals, and for L is equal to 2, you get the d orbitals. Of course, for L is equal to 0, you get the s orbitals, which corresponds to 0 angular momentum and no nodal surfaces whatsoever. But for L is equal to 1 and 2, you will get these kinds of nodal surfaces, which will help you understand the orbital structure a little bit better. How? You see, right now we're just looking at the spherical harmonics. There are supposed to be L number of nodal surfaces. So whenever we have L is equal to 1, okay, whenever we have L is equal to 1, if you compare these diagrams, they are ultimately the result of standing angular wave patterns on the surface of a sphere whose magnitude is shown as, or which magnitude square is shown as outward radial direction. That's why you end up getting these lobe-like structures in that direction where the magnitude is finite. Otherwise, it goes to 0. Here, the magnitude is finite. Here, the magnitude is finite. You get these structures. But dividing these structures, you end up getting these nodal planes, right? These nodal planes correspond to 0 value of the spherical harmonics. Therefore, the overall probability density there is going to be 0. Same here, same here. How many such nodal planes exist for L is equal to 1? 1 each. 1 nodal plane, 1 nodal plane, 1 nodal plane. So the entire structure has been sort of sliced by a nodal plane of 0 probability density. If you go to L is equal to 2, these cases, right? For the case of L is equal to 2, then you end up getting 2 nodal planes. Of course, I'm taking the real spherical harmonics here. So 1, 2 nodal planes. Here also you have 1 and 2 nodal planes. These 2 cones represent 2 separate nodal planes. These 2 separate nodal planes, and on and on. So as we go higher up in the value of L, we are going higher up in the orbital angular momentum, and we are also going higher up in the winding of the standing waves on the unit surface, the angular standing waves of the unit surface. Thereby, we end up getting more and more nodal planes. 2 nodal planes here for L is equal to 2, right? And when we combine this structure, with our radial solutions, we will then get the final probability density shapes. And I want to show that shapes in 2D manner because the radial solutions simply represent shell-like structure. In 3D, it's a little bit difficult to visualize unless you have a cross section. So I'm going to combine these diagrams in a 2D plane, the radial probability distribution and the spherical harmonics probability distributions to get the overall shape, which looks something like this. Okay, here it is. Okay, let us try to appreciate what we have achieved today. We have together achieved something really beautiful. Okay, we have actually obtained the shapes of the electronic probability configuration for the smallest atom in our periodic table. So for the ground state, basically, you end up getting a simple blob. Yeah, you end up getting this radial distribution, right? Probability distribution. And because for L is equal to 0, it's just a constant surface, so that doesn't really affect anything. You get a spherical shell type of a blob, right? Now, when you go higher up, so for N is equal to 1 and L is equal to 0 here, and this is N is equal to 2 and L is, when you go higher up, so for example, here we had, this was N is equal to 1, all of this is N is equal to 2, and all of this is N is equal to 3. This is L is equal to 0, this is L is equal to -1, +1, and 0. And similarly, this is 3s, and this is 3p's, and this is 3d's. Okay, I hope the text here is clear to you. And we end up getting a superposition of the radial solutions and the spherical harmonics, right? So if you look here for, let's suppose, 2s, you end up getting effectively 2 shells like this, 2 shells of probability densities. If you look at the 2p orbitals, you end up getting, because for 2p, the radial solution simply introduces a single shell, okay? And the spherical harmonics introduces these dumbbell shapes. So you effectively get these dumbbell shaped distributions. You see here, okay? You see these dumbbell shaped distributions here, okay? Like this and like this. And these white lines, they represent the nodal surfaces where the probability density has to be 0. And therefore, you end up getting these dumbbell-shaped structures. For 3, you get 3 distinct spherical, for 3s, you get 3 distinct spherical shells. And for 3p, you have, of course, the shell structure that introduces a nodal plane along the radial direction, and the p orbital structure that introduces the nodal surfaces along xyz directions. Yeah. And for D, of course, you end up getting these beautiful surfaces. Now keep in mind that the energy levels only depend upon n. So therefore, here the energy level here is going to be minus 13.6 upon 1 electron volt. Here it is going to be equal to minus 13.6 upon 2 square electron volt. And all of these, its energy level is going to be minus 13.6 upon 3 square electron volt. Okay, because the degeneracy is n square, as I have proved earlier. So basically, we are going higher up in energy. And as we go higher up in energy, even the sizes of the orbital shapes are kind of increasing if you take a look at the size, because the expectation value of the radius is increasing with n square. Yep. So there you have it, a complete description of the wave function solutions, the probability density distributions, the energy levels, and everything in between from start to finish using Schrodinger's quantum mechanics for a hydrogen atom.